you see how it's not the clean, pure shape that we had in the other models. See how its belly is really hanging out. So very painful experience again. But it worked, it was strong. You could sit on it on top without a problem. But the problem was not there. That's where you had the strong arches. The problem was here, where you could see that it was really starting to slump. In the areas where, so here we have a triangulated grid, and here at the bottom we would have quad shapes, but here we would have three overhanging members, and that's where it became really weak, as you can see here. But the installation sequence worked, the effects worked. The only thing that we need now is to find a way to solve this problem, and the way we did that is by suspending some of these key points from the stronger points above. So in the next models you'll see that. But here you see how it's really actually being squeezed in under its own gravity. Which got the structural engineers very nervous, by the way. So then we did the final digital model, and it's a bit hard to see, yeah. So in this digital model, that's the final one that we use for construction. So to give you some numbers, 350 square meters, 200 people can easily sit underneath it. This is 37 meters. And the height of the arches is, what was it? Sorry, the top is 12.3 meters, so it's really big. You can really fit this whole floor and everything easily underneath it. And then at night it's made from these three layers, so you get that nice deep effect. We built prototypes from that again, this time really using everything that we were going to use on site. We figured out that what the maximum transportation lengths were for bamboo, for example, so all these parameters are now fed into the model, and that's the 1:20 scale model that you can see there. We put a skin over it, and here you see the metal wire that I was mentioning that's used to suspend the belly from the top. That worked quite well, so you can see a little bit cutting across. We did a scan of that project, of the model, scaled it up to compare it with our digital files, and here you see how close we are. Scaled up to full scale, we're actually primarily below 5 centimeters of deviation in a 1:20 model, which means, was that 2.5 millimeters, which is really, really close. Only in one area were we bigger, and that's because one of the sticks broke. So this gave us enough confidence that our digital assumptions were correct, that we could go ahead with that. So then, the real deal, construction. So we work with Maozu, which is a giant bamboo species that's indigenous to China. They have similar bamboo species all across the world, so the concept that we have here could easily be translated to Brazil or Colombia or to Black Africa or something like that. Anyway, this is where the bamboo grows. It's all being centralized in this part. And back in the day, they would transport the bamboo by river to Hong Kong, where it would sit in the water for a few weeks before it's being used. Nowadays, that doesn't happen anymore. They just collect it in the factory. These are the bamboo forests. If you've ever been to Kyoto to see the bamboo forest that they have there, this is nothing like that. This is much more messy and uncontrolled. So we had to really rely on the local people to tell us what it was that they were cutting for us. So here you see very fresh bamboo. And when it's fresh, it's green, it's quite flexible. When it's young, you see that it has a relatively shallow thickness. So bamboo can be harvested between 3 and 5 years, 3 to 7 years. 5 years ideally, and after that it just gets too dense and it starts to wither away like grass. So it has a life cycle, but the middle part is really easy to use in construction. It's brought into the central collection point, and here you see all the poles. So the first thing we did was get rid of the really wonky ones that we didn't use, and then around that time we had a problem at the university. Our scale model was being eaten alive by bugs. The problem with bamboo is that it's very high in sugar content. It's very desirable for insects and for biotic attack. And back in the day, when they were transporting the bamboo over the river, storing it in ocean water, the salt of the ocean water would basically wash out the sugars and replace it with salt inside, making the bamboo no longer easily digested by bugs. So we needed to do a similar treatment. There's many ways to treat bamboo. The one that we selected was this, which is where we would submerge the bamboo in a borax and a boric acid solution, which are natural salts. Our contractor had never heard of that and was very resilient to even try that, but we had contractually agreed to it, so he was forced to do it. And the method that we had prescribed was that they need to make these big containers in which they were going to make a hot salt solution so that we could submerge things in there to speed it up. And the first thing that we need to do is to perforate all the diaphragms of the bamboo. This is what we have here. And then they would be submerged into these bathtubs. Now, if you've ever tried to dissolve sugar in cold tea, that doesn't work. You really need hot tea to dissolve your sugar. Similarly, we need to have hot water to dissolve our salt. The way they were going to heat up their water, I don't know if you can tell, was by these deconstructed rice cookers. And they were going to use to heat up this whole vat. So of course that didn't work. After a while, they realized it wasn't going to work, so we asked them to bring some oil barrels. And the idea was that we're first going to heat it up and dissolve the salt in a smaller quantity, and then put it into the main thing. So here's them again, trying to make this barrel of hot water heat up, which didn't work. We told them they need to put a fire underneath it. They didn't want to do it. They wanted to do it with their coils here. So my guy, who you can see in the reflection, got electrocuted 3 times trying to set this up. Very dangerous, so it didn't work. In the end, they said, we'll do it with cold water. We said, it's not going to work with cold water, you need hot water. They said, yeah, it's going to work with cold water if we use a concrete mixer. So they tried to use a concrete mixer to mix in the salt, and I don't know if you ever tried to dissolve sugar into cold tea, no matter how much you stir, it doesn't work. So it didn't work. So eventually they agreed with us, and they allowed us to just chop up some bamboo and make a little fire. And this is again, thank you that we're in China, because this beats all safety requirements that we have in Hong Kong. So again, with the concrete mixers, absolute safety hazard. They were heating up these barrels, and in no time the salt was dissolved. We siphoned, these are the biggest flip-flops you can have. They siphoned the water into the containers, we submerged the bamboo, and once one tub was done, we siphoned the water off to the other tub, got the bamboo out, cleaned it nicely, and that was it, the bamboo was treated. So in principle, if you treat your bamboo for a biotic attack, you protect it from direct UV light, and you make sure that it isn't in contact with water at all times, so rain or stagnant water, then it can last indefinitely. You can make permanent buildings with it. So we designed this project to be permanent. The design took all these requirements into consideration. While that was happening, we were building the foundations on site, and that's where the sailboat comes in. I don't know if you've ever seen these Volvo ocean races. Really fantastic, magnificent boats going at super high speed through the ocean. That's the dimension of one of these boats, so 30.3 meters, 12.5 tons, 578 square meters when they go downwind, so that's their biggest sail. Our structure weighs roughly half, is bigger, and it almost has twice the amount of area. So you can imagine, if we need to build something that's typhoon-proof, the force of uplift that's pulling on this structure is vast. So a very important and crucial connection is when the bamboo touches the ground. So we had a skin around the whole thing that was a tension membrane. That skin was to be connected in every crossing with the bamboo, but the transfer of that load down to the foundation was very, very important. To give you some numbers, the whole structure above my hand weighs 6.7 tons. The air underneath the structure weighs 4.3 tons. So the structure is only 60%, 70% heavier than the air that it contains. So it's a hyper lightweight structure. Then these 3 slabs together weigh around 100 tons just to hold it down. So that's 16 times heavier than the structure above it just to hold it down. So the detail that we came up with there is inspired by a detail that we found in Colombia, where for their vernacular structures, what they do is they get these big rocks, they drill a hole in it, they put a rebar in it, put some non-shrink grout next to it, and then they cast the rebar into the bamboo. So we wanted to do something similar, where we have the concrete slab here, we put the rebar above it, we bend the rebar, and then here you see that, similar to how you have the ripples on the rebar to create the friction between the concrete and the rebar, we use the profile of the bamboo itself to create that friction back to the bamboo. So a very simple detail, very easily drawn, but much more difficult to build, because all these sticks are going in different directions, and we needed to make sure that it was according to our digital file. So, basic slabs, these little fins in there were to prevent the whole structure from sliding open on the grass. Standard concrete casting, pretty straightforward, and these were the rebars that were sticking out. First challenge, first major fight with the contractor on how we're going to bend them all. In the end, we solved it with a simple steel pipe and an A3 sheet of paper that we had cut according to the correct angle. And here you see them bending it. Yeah, that's good, close enough. So that's CNC paper printing. So here we had all the rods in the right direction. And then these little plinths that had, so the bamboo had to sit on a perpendicular plane, because otherwise it would just split again from different load transmissions. I cannot tell you how much money the contractor had put into their fee for these little plinths, but it was a lot. And it was a huge headache because again, they're all different. We were speculating on how we're going to do this, I don't know, whatever CNC production. In the end, we just did this. We took some plastic sewage pipes. We just cut them according to angles that we extracted from our digital files using a simple Excel spreadsheet. And then all they had to do is slide it over the rebar, fill it with cement, and there you go, perfect plinth. You can even do these complex Boolean operations with them by hand in no time. So very simple, very straightforward. So we saved the guy a lot of money. So here you see the bamboo arriving. We first cleaned the bamboo, we protect it from the sun, and we sort it all nicely. So that's the bamboo structure. So 473 poles, 3 kilometers roughly, and so these poles at the base were around 12 to 15 centimeters, and at the top 8 to 12 centimeters, and each and every one of them weighs around 20 kilos, which is enough for one person to carry, but there's no way you're going to be able to bend them by yourself, except when you connect them all into long members, then they become very flexible. So the idea here was that we're going to replicate this digital file. And digitally, we could extract every single coordinate very precisely to the millimeter. But the challenge was, again, how do you deal with these bamboo scaffolders that don't weak plans? So similar to the Golden Moon, we built up on that and took all of these members, digitally unrolled them, marking up each panel, each stick with a specific number, and marking up the intersections of where these different directions would meet up. So we printed this big sheet of stickers where, for example, here you see, this is the label for pole C14 intersecting with pole A2 and B14. Every sticker label is unique, and then all they had to do is make sure that they don't mess up in the annotation. So here you see them taking the stickers, labeling each pole, cutting it to the correct length, and then with bamboo again we made this 40-meter long table upon which they would just line up all the poles. This is the black glass fiber plastic that they use for the normal traditional tie, but we replaced it with metal wire to make it fireproof. So here you see them connecting everything in one long stick, and then using our construction drawings, and these were the only construction drawings that we used, these unrolled spreadsheets, to measure things up. Accuracy got, I don't know, 10 centimeters, 5 centimeters, to put those sticker labels up. And while they were doing this, they built a temporary scaffold, and then all we had to do is slowly hoist up these members, slide it over these guides, and try to get it onto the structure, slide it over its feet. And here you see how big that leg is, how thin each and every one of these members is. It's super thin. Now the first, I don't know if you remember from the little video where you saw the sticks jumping on top of the scaffolding digitally. We knew that the first, say, 9, 10 sticks we need to have them pretty accurately. So for those, we projected some of their intersections down to the ground, where you see the coordinates of the intersection point higher up, measured from the centers of the 3 concrete slabs. And then there, we put up a vertical marking as well, where we knew exactly where a pole needed to be at that particular location. Only for the first dozen or so poles. Later on, we could rely entirely on the intersection markings that were already in place as guides to install it. So you see them putting things up, sliding it over the starter bars, bending it into place. So here you see roughly the first poles that were marked up on the ground. Here you see them just manually, using no steam bending, nothing, just manual force and a huge lever to bend things into place and then fix it at the side. Simple wedges and jigs to put things in place. And here you see what one point in our digital model became in our physical model. So these are the metal wires to tie everything together. This is the curvature that you're getting on, so it's quite something. And here you see the deviation that we have. So one point became basically a 20 centimeter diameter cloud of approximation where these members are trying to meet. This is the same view from above, so you can see how far off we are. But it didn't really matter because the system is self-correcting. As long as the whole principle is in place, eventually it corrects itself. We could never incorporate all the diameter deviations from each and every one single pole. So we had to allow a little bit for that. So what that meant was that sometimes at the base we had a bigger gap. Sometimes our poles were a little bit too long, then we could just cut them off. With the gap that we had here, we needed to solve in the fixing detail. So that fixing to the foundation now, pretty straightforward again. We drilled in these anchors. We first pulled the pole to be nicely centered onto the starter bar, and then we used the same plastic sewage rings that we used before to clamp around the bamboo so it wouldn't split when we drilled a hole in there. And then we sealed off the base with, again, the same plastic pipes. And then we invented this very sophisticated tool where we cut up a fire hose and made a funnel on top, and we're just pouring in grout, and then so you manually had to sort of, I don't know, milk or jerk that concrete into the pole, which was quite a view. This guy was laughing the whole time. So anyway, you could knock on the pole to hear when it was full, and once it was full, you saw the bamboo being filled. The bottom, perfect connection. We added these spanners just in case, if the bamboo were to split, that it cannot just slide off and go up. So here you see the complexity of the different directions, totally absorbed in a simple detail. 3 members meeting, and here the longest correction that we had to do. Then all we had to do is fill up the holes. We had carefully numbered everything. Nobody ever saw this because this was all behind the fabric, but we put the right plugs in the right holes, fetishist as we were. And then the big challenge was the release from the scaffolding. I didn't point this out, but when we did the model on our rooftop, the one that was sort of